And we want to pick up right where we left off in Chapter 9 and start to talk a little bit more about how we can track the energy that is given off or taken in by these chemical reactions, and then be able to make predictions, use those numbers to make predictions about other chemical reactions. So we'll start off with a definition of the thermodynamic standard state. And so the standard state is the most stable form of a substance at normal pressure, which is 1 atmosphere, and a specific temperature. And normally standard state is considered to be 25 degrees Celsius, that's 77 Fahrenheit. And if we're talking about a solution, we consider it to be 1 molar solution. And so when you see a standard enthalpy for a reaction in a textbook or in a table or a data table somewhere, that is the enthalpy change that was measured for that reaction or calculated for that reaction under the conditions we just described, standard conditions, 25 degrees, 1 atmosphere, and 1 molar for concentration of solutions. Now, if we look in the back of the textbook, there will be several different tables, some of them are several pages long each, that give us different enthalpies. The enthalpy of fusion is the amount of heat necessary, these are going to be positive numbers because it's heat being put in, to melt a substance without changing its temperature. So for water, this would have to be done at 0 degrees. For gallium, it would have to be done at 30-some degrees, which is the temperature at which gallium melts. But this is the enthalpy that's required, the amount of heat that's required to melt a substance. Enthalpy of vaporization is just like that, but it's the amount of heat that's necessary to vaporize a substance without changing its temperature. And that one is a little bit more forgiving from a temperature standpoint. We need 100 degrees Celsius to boil water, but we can certainly evaporate an entire water sample without raising the temperature that high. It'll just take longer, but it will evaporate at low humidities. Enthalpy of sublimation is the amount of heat that's necessary to change a substance directly from solid to gas without any temperature change. There are some substances that do this naturally at normal conditions, like CO2. Go over to Kroger, you can buy dry ice. It looks a little bit like ice, but it's white, maybe a little bit more brittle than ice. But you'll notice it never melts, it just vaporizes, or better term, sublimes. It turns directly from solid to gas. If you do go buy that at Kroger, be careful how you handle it. It's much colder than ice and can give you frostbite or freezer burns on your skin if you touch it. Now, I mentioned earlier that delta H's for all those processes on the previous slide are going to be positive. That's because we have to put heat in. The reverse of those processes would be have negative delta H's. So if a process gives off heat, if we don't have to put heat in to make it happen, but the surroundings get warmer naturally when that process happens, we call that an exothermic process. Whereas an endothermic process is a process we have to put heat into in order to make it happen. So evaporation is an endothermic process. If you spill rubbing alcohol in your hand automatically starts to feel cold, even though that rubbing alcohol is at room temperature. And it's because the rubbing alcohol is evaporating quickly. Same thing with nail polish remover. It feels cold because it's evaporating and it's pulling heat out of your hand. Your hand is putting heat into that process because it's an endothermic process. Any process that happens and is endothermic, the reverse is exothermic. Any process that's exothermic, the reverse is endothermic. And so we'll have two different kinds of calorimeters that we want to be able to use to measure changes in heat. A constant pressure calorimeter, which sometimes we'll call a coffee cup calorimeter, is one where the top is open enough or expandable enough that the pressure stays the same no matter whether there's gas generated or heat generated or not. And we can measure delta H directly by looking at temperature change of the system and of the surroundings. A bomb calorimeter, and this is, I mean, we maybe need to come up with a better word to describe this nowadays because that term freaks people out. But a bomb calorimeter is one that has a constant volume pressure. It'll hold up to a very large amount of pressure change without changing its volume significantly. And so when we do our calculations from data we get from a bomb calorimeter, we're not calculating delta H. We're not calculating Q. We're calculating delta E because we're not allowing any work to be done, any expansion of the system. But you can see they look very similar. The difference is the lid. This would be a very stiff container, and the lid would fit very tightly, whereas on the constant pressure calorimeter, the lid would be loose and would allow gas in and out so that the pressure would be constant and would allow expansion to happen. Another definition on how we're going to track energy changes: heat capacity. See, we're going to have to measure how the temperature changes for a particular item and then use that to calculate how much energy was transferred. In order to do that, we have to know how difficult it is to change the temperature of something. So that's its heat capacity. Metals tend to have very low heat capacities. It's easy to change their temperature. A little bit of heat will heat a metal up a lot. But water and bricks and some ceramics have higher heat capacities. It takes a lot more heat energy added to change the temperature of those objects by the same amount that metal could be changed with a small amount of heat. So heat capacity is going to be defined as delta H or Q, the amount of heat energy that goes in, over delta T, and it's a conversion factor for a particular substance. And so we can rearrange that equation and get Q equals C times delta T. The trick is that this conversion factor is object dependent. In other words, it depends on mass. A big piece of metal is going to require more heat than a small piece of metal to change the temperature by the same amount. So to get more specific and to have a better conversion factor that's usable all around, we define this term specific heat, and that's the amount of heat required to raise the temperature of 1 gram of any particular substance by 1 degree. So we'll call that SH for right now. Q is specific heat times mass times delta T, where Q is the amount of heat that has been transferred to the material that has this specific heat and this mass, and that heat causes this temperature change. Molar heat capacity is similar. The specific heat is the amount of heat required to raise the temperature of a gram of a substance 1 degree. Molar heat capacity is the amount of heat required to raise the temperature of a mole of a substance by 1 degree. So you see in the equation, molar heat capacity replaces specific heat, moles replaces mass. So we can take a look at the specific heats of these things. Air has a specific heat of about 1 joule per gram degree. So it takes 1 joule of energy to raise the temperature of air, a gram of air, by 1 degree. Aluminum is easier to heat per gram, even though it's denser. Copper is even easier. It's got a lower specific heat. Gold has a very low specific heat. So if you have a cold piece of gold, you could put a little bit of heat into it and it would start to get very hot. Whereas water as a solid, ice, has a specific heat that's twice as large as air and what looks like about 15 times as large as gold. And liquid water is twice as hard to heat as that per gram. Now look at the per moles. The molar heat capacities for all the metals are about the same. They run between 24 and 28, whereas salt and water are still higher. So the per mole heat capacity is fairly constant across most metals. All right, so here's a quick practice example. What is the specific heat of silicon in joules per gram degree if it takes 192 joules to raise the temperature of a 45 gram block of silicon 6 degrees. And what is the molar heat capacity of silicon? So let's fix that grammar error right there, or spelling. All right, there we go. Let's take a look at how we would do this problem. We said that Q is mass times specific heat, probably should have used SH here, times delta T. So we can rearrange that specific heat is Q over M delta T. We were told Q, the amount of energy in joules, is 192. We were told mass 45 grams. We were told the change in temperature was 6 degrees. And this all goes in our calculator, and we get the right units for specific heat. Now, specific heat's units are joules per gram degree. So if we write that down, and we want molar heat capacity, or molar specific heat for silicon, then we have to convert that gram that's in joules per gram degree to moles, so that we'll get joules per mole degree, since that's the unit for molar heat capacity. And so the way to get grams to cancel in the denominator and get moles in the denominator is to multiply by molar mass. And the molar mass of silicon from the periodic table is 28.1. And 0.71 times 28.1 gives us 20 joules per mole degree. And we're going to take a break right there and come back with Hess's law and some kinds of calculations we can do on delta H for the last video of this chapter.